Okay, so I didn't get to talk about fish last week, so I wanted to go ahead and include this slide. The two slides that I have are photographs of fish do a horrible injustice to the diversity of fish species. Boy, I think Wikipedia will give us an estimate of the fish number of fish species as something of around the order of 15 or 20,000. You can check me on that, but it's in that order of magnitude. Very diverse group of animals. What I'm trying to represent here is just a couple of things, some of the most popular fish that we see in the marketplace, and as well as some of the distinct differences between those fish. So, for example, here's herring. They're very small, right, versus carp, which can be enormous, as well as tuna, which can also be very enormous. While we're mentioning tuna, tuna itself is a very diverse group of animals. They're fast swimmers, they're constant swimmers, they migrate for very long distances, and they have high concentration of myoglobin. They are considered a dark fish. Most of the fish on this page, herring and carp and cod, I believe, are oily fish, even though a cod would be considered a white fish. So again, the distinction between what's white and dark is a little bit funny. And then of course there's salmon, which are neither white nor dark. Certainly not dark because of myoglobin, but we do associate salmon with this sort of reddish colored flesh, and that's not has nothing to do with myoglobin or mitochondria, as we'll see in a moment. But these are Pacific salmon, right? The Pacific Northwest in particular. They're so-called anadromous fish because they live part of their life. They're born in freshwater and then head out to sea and then migrate back to their birthing grounds for spawning. So they live part of their life in salt and part of their life in seawater. There are trout species that are not anadromous but are nevertheless related to those salmon. They live in freshwater all the time. So we got oily fish. We got white oily fish. We got white non-oily fish. We have dark fish. We have interestingly colored fish. Lots of fish. Oh, yes. Okay, here's some more. These are mostly white fish, I believe. Again, not. I'm only drawing some highlights here. Flatfish, such as halibut or flounder, are very popular fish. Bass as well comes in both sea and freshwater varieties, which can often interbreed, leading to the striped bass. I believe is a hybrid. Swordfish, uh, there's an interesting fish because of it's overfishing and depletion of the population, as well as its tendency to accumulate mercury. And I'll come back to that in a moment. Perch, of course, is a fish we're familiar with. I'm mentioning red snapper for the interesting reason that here's a red snapper, and I think there's some Atlantic species of red snapper, and then there's some in the Gulf of California. I mean the Gulf of Mexico. Hopefully, the red snapper population is not going to be adversely affected by the recent oil spills there. Um, why I mention this though is that the the way fish are presented in the marketplace uh, can be very confusing. For example, you'll frequently see red snapper sold in West Coast grocery stores, but those are not true snappers. Those are actually a species of rockfish, which are themselves a very diverse group of fish. So, but they have a similar exterior coloration and maybe a similar texture and flavor, and so we call them a red snapper. I should have introduced a slide. Red snapper is a wonderful fish, and there are several Mexican dishes that make excellent use of red snapper. My favorite is huachinango veracruzana. Huachinango is just that. I suppose a Nahuatl word. I can't say that with any certainty. For the red snapper. And huachinango veracruzana is a wonderful baked fish served with olives and tomatoes. Oh man, it's really good. I'll try to introduce a photograph of that in my next lecture. And Patagonian toothfish is another interesting one that I just introduce because of this idea of representation. Chilean sea bass um, is a very popular food item in many upscale restaurants. It is not a bass. It is a Patagonian toothfish, an entirely different kind of fish, a deep water sort of Arctic fish, and it is heavily overfished. So again, the way we decide to market things is very important and can have severe effects on the ecology of those organisms. One issue that I want to touch on as well is the question of fish, farmed or wild. This takes us back a little bit to salmon. You probably are familiar with, you're in the grocery store seeing farmed salmon, farm-raised salmon, or wild-caught salmon. What's the difference? Well, let's talk about it. So the pigmentation of salmon, that reddish pigment or pinkish pigment, is due to a molecule called astaxanthin. That's a carotenoid pigment, right? Think of beta carotene. That is derived from the wild diet of these salmon, the salmon of the wild, the diet of the wild salmon from these microalgae that themselves produce the pigment. So the salmon itself is not producing that pigment, it's just being deposited in their tissues as a result of consuming that algae. The farmed versions the farmed animals are not exposed to those algae, and so they have no pigmentation, looking a little bit like a trout, right? Think about the difference between a salmon and that non-anadromous trout, right? Pink versus less pink or not pink. That's again because the animals that aren't going to sea aren't being exposed to those microorganisms. In order to achieve that pigmentation, right, you have a hard time selling salmon in the grocery store if it wasn't pink. The animals are fed a synthetic version. Here, that synthetic version is sold by, among other companies, Roche, and here's a great picture of their so-called Salmofan. It tells you what intensity of pigmentation you can achieve by what concentration of the pigment you place in the food. For the chemists out there in the audience, it's easy. There's some easy chemical analyses that you can do to determine whether it's farmed or wild truly. So there's a little bit of truth in advertising for you. The difference between, well, let's take a closer look at astaxanthin. Here's the molecule. There's these sort of phenyl groups here. There's one chiral center at each place, and for the non-chemists, all that means is that that carbon is bound to 4 different substituent groups, making that a sort of a special atom around which there is defined symmetry. So if we looked at the mirror image of this molecule, that would be a slightly different orientation of that OH or that hydroxyl group, for example. So the chirality, there's 2 chiral centers, and what that means is that we can have 3 different versions of this molecule. One in which the hydroxyls are oriented in one direction, one in which the hydroxyls are oriented in the opposite direction, and then one in which one hydroxyl is oriented one way and the other is oriented in an opposite way. That gives you 3 different versions. The interesting thing is that in the wild, right, biological biosynthetic systems are only going to create the all one or all the other. They're not going to create the so-called meso compound. It just doesn't happen, and it's a little bit beyond our scope to discuss that in the context of this class. But what that means is that you can check farmed animal tissue, and they should have all 3 versions, because in the organic synthesis laboratory, you'll get all 3 types. So it's very easy to distinguish between what's really farmed and what's wild. And in fact, the reason I mention it is that there have been some sort of non-scientific studies aimed at identifying how frequently wild-caught salmon is misrepresented as such and is in fact farmed, and it can be as high as 10%. So, when you're making the decision about whether to spend that $20 or more a pound on the wild-caught salmon, think about whether there's truth in advertising. Also, in terms of farmed fish, let's think about aquaculture. So here's a sort of a generic stock photograph of a fish farm it's a sort of protected inlet. This is a salmon fishery. There are positive aspects, right? Typically, aquaculture provides a uniform product, right? The fish are the same size, they're the same quality. That's very useful for vendors to sell to marketplaces. There might be fresher. That is, the distribution systems are much better organized, and you can get the product from the farm to the marketplace much more rapidly. And they can have a lower parasite load than wild fish. Certainly, they would have a more uniform parasite load. Whereas the fish that the salmon that you're catching in the wild have their own life history that will determine what kind of parasite load they're carrying. Now, that's not to say that salmon that are farmed, or other fish that are farmed, are parasite free. By no means. But there are some cons as well. Fish farming can result in increased pollution of nearby waters, and that can be because of the feed that's increasing the nutrient richness of the surrounding waters. It can also affect the genetic diversity of the natural population of fish in that region. For example, the salmon that are farmed in the Pacific Northwest are not Pacific salmon; they are Atlantic salmon, and it's conceivable that there could be some contamination of the genetic heritage of those Pacific salmon with the introduced or farmed salmon. And there could be the introduction of new parasites. Again, if we're bringing in a species of fish that's foreign to the region, they might bring their own parasites that can then establish themselves in that new region. So there's interesting questions to think about as you're walking down the aisle in the grocery store. Let's talk for a minute about fish tissue, white versus red again, or light versus dark meat. White fish are intermittent swimmers, right? So they're going to be mostly stationary, but they're going to have to get away from predators in a hurry. So that's fast twitch muscle, low oxygen storage capacity, and therefore low myoglobin concentrations, and therefore lighter coloration. Darker fish like tuna, very active predators, and also migratory in many cases, and they have a higher proportion of these red muscle fibers. And in fact, if you look at tuna before you cook it, at least it's a much darker tissue. Let's see. Aside from the coloration of the fish tissue, something that we usually associate with fish as compared to beef or other mammalian or poultry tissue, muscle tissue, is how light and flaky the texture is. And this has to do with the way that the muscle is organized. As opposed to the structures we talked about for red meat, fish tissue is usually organized into these very short myotomes. And here's an example of the myotome, right? And each myotome is connected to the next with a layer of connective tissue. Low collagen content in that connective tissue, but of course, just like with red meat, the amount of connective tissue is going to determine the texture of that fish. And I would say compare rockfish or red snapper to shark or swordfish to get a sense of the differences or the extremes of texture that you can achieve or that you can find in fish. Anyway, these short myotomes make for the flakiness, the flaky texture, as opposed to long muscle fibers in beef, for example. The other thing that we think about when we're contemplating a fish meal is the fishiness or the fishy odor of that tissue, and that usually derives from the chemicals trimethylamine oxide and urea, and not from those in particular. Those molecules are beneficial to the animal in so far as they reduce the osmotic tension. So what is osmotic tension? Well, it has to do with the pressure that a cell feels because of the relative concentration of water and salt within and without of the cell. To compensate for those high salt environments, fish will have a high concentration of these chemicals. When the fish is killed, those chemicals begin to break down into trimethylamine, which has a strong odor, as well as ammonia, which obviously has a strong odor. So the degradation of these chemicals is what gives rise to that fishy flavor or fishy odors, and those we associate with or negatively with fish. Many people cannot tolerate those, and so they don't eat much fish. I think this is the last thing I'm going to say about fish, and briefly talking about some nutritional and health concerns that we hear frequently about fish, just touching on the surface of these issues. Omega-3 fatty acids are something that has become sort of a dietary fad, considered to be very important in neural development and also in limiting the action of certain inflammatory chemicals. We won't go into the biochemistry of that, but just suffice it to say that there are lots of signaling molecules are derived from fatty acids such as this one. One I've drawn here for you is eicosapentaenoic acid, ICO for 20. There are 20 carbons in this structure. We'll look at that again in a moment. Pentanoic, there are 5 unsaturated bonds along the chain. Um, I'll come back to the idea of the importance of omega-3s, but first of all, let's just look at some fatty acid nomenclature. So remember, it's a long, nonpolar, oily chain of carbons, and at one end there's this acid group, so it's a fatty acid. Omega-3, well, the first carbon after the acid is called the alpha carbon, and then the omega carbon is the final carbon. There are lots of ways of discussing fatty acid, or there's lots of nomenclatures out there for fatty acids, but omega, when we refer to an omega-3 fatty acid, we're referring to the third carbon, 1, 2, 3, in from the omega, and that's the first carbon at which there's a an unsaturated bond. So at omega -3, there's a double bond, and in this case there are 5 in a row, or 5 separated by 1 carbon apiece. Highly unsaturated, and you can think back to what you think this would mean for the relative melting point of this fatty acid. Hopefully you remember that unsaturated fatty acids are going to be more liquid-like and less fat or solid at room temperature, and that's because of the difficulty of packing these highly kinked structures together. But again, omega-3s are considered very important and nutritionally nowadays, for their role that they play in the development of neural tissue, their incorporation into lipid bilayers of neural tissue. Egg yolks, I think I might have mentioned at the beginning of the semester, are also a good source of omega-3s, as of course are fish oils. So in addition to some nutritionally valuable oils, we also worry about toxins in our fish, and introduce the words bioaccumulation and biomagnification. Bioaccumulation tending to mean the propensity of an individual organism to accumulate a particular compound, in this case toxin, in its tissues. Magnification being the magnification of the importance of that toxin higher up the food chain, among other things. So the idea for us is to go back to the example of swordfish, which are known to be high in mercury concentration, and that's because of their position on the food chain. Usually mercury takes the form of methylmercury, and this is known to play a role in impairing neural development and other neurological effects. So high concentrations of mercury. This is why we'll avoid certain kinds of fish, not others, right? Herring, for example, has relatively low mercury, generally has a very low mercury concentration. So it depends on where on the food chain we're finding our fish in terms of what we need to be worried about. And that, again, it relates to this idea of biomagnification. Another great example of that, of course, is the bald eagles, which tended to biomagnify the DDT in the environment, and that had the adverse effect of softening their eggs. So, mercury polychlorinated biphenyls. These were introduced earlier in the 20th century, in the electrical industry, particularly in transformers, for their electrical characteristics or properties. Lots of acute effects, but these molecules are nasty organics, and they tend again to biomagnify and can induce liver damage in humans. Enjoy, and we'll pick up again with what are we doing next? I think sugar's coming up and chocolate. So I'll see you again at the next lecture.